Hi everybody, my name is Linas Beresna. I'll be presenting our joint work with Eugene and Fiume from Simon Fraser University. I'll be presenting our work on glare mitigation using a differentiable unified glare rating. The one-line version is that we take a perceptual lighting comfort metric, so here specifically the unified glare rating, and make it differentiable so it can drive an inverse rendering problem instead of just being a measured quantity. So starting with the problem and what glare is perceived as excessive brightness. It causes discomfort and degrades visual performance. And in architecture, it is a real design constraint, not just an aesthetic nicety. Industry quantifies it with a CIE unified glare rating, which underpins standards like the EN 12464, for offices and other indoor environments and workspaces that need to be built and designed to a specific code. However, the way that it's used and evaluated and optimized typically in design spaces today is in a post hoc fashion. So you render the scene, you measure the UGR, the unified glare rating, you manually tweak material lights or parameters, re-render and repeat until you get your specific score that you want. And so this trial and error loop can be quite slow, and it gets worse the more complex the scene gets, or the more complex the light transport gets, or the more material parameters that you want to change. So we want to replace that loop with gradients, and hence use gradient descent via a differentiable renderer. So here's how glare is actually evaluated on an image. From a render, we can compute a per pixel luminance map, so the image on the left, and then using that, we can classify which regions count as glare sources, giving the mask on the right. So these two ideas are quite important. They tell a picture of glare and hence unified glare rating in the scene. The map on the left is a continuous luminance field, and it allows the creation of a discrete classification of what counts as glare. Now moving on to the metric itself, UGR, unified glare rating, aggregates over all glare sources their squared luminance weighted by two spatial terms. One, the solid angle of what each source subtends, and then the Guff position index. The position index captures a well-established perceptual fact that a bright source is far more disturbing in your line of sight rather than being off in the peripheries. And so it weights each source by its angular displacement of the gaze and penalizes the more it's within your range of view. And the maps on the right show those weights in specifically camera space, and then we take this glare source amount and it's divided by the total adaptation luminance of the scene, so the background luminance. So the most important thing to see here is that UGR is a contrast ratio. Its sources are measured against the background luminance, not just absolute brightness or hotspots. So why can't we just plug this into a differential renderer and use it? The problem is that a pixel only counts as a glare source if its luminance exceeds a specific threshold of the background luminance. Typically, it can be 5, but we can use any number here. And it creates a hard binary threshold. Mathematically, that can create a step function, and its derivatives become almost zero everywhere else apart from the specific hotspots. And it creates a spike specifically at the boundary. So differentiable renderers can struggle to use these non-existent gradients. So our approach is to replace this discrete metric with a continuous, fully differentiable proxy. And once we do that, gradients can flow from the perceptual rating back through the path trace light transport and back into physical scene parameters. So that being roughness, reflective indexes. So this turns UGR from a passive number that you compute into an active loss landscape you can descend and use to optimize a scene. So to the best of our knowledge, this is the first time that we've used a visual discomfort rating directly embedded into a differentiable renderer. And there's two ingredients that make that work. I'll take them in turn. So ingredient one is that inverse rendering typically runs at quite low sample counts. So it can be around 16 samples per pixel, maybe higher, in order to stay tractable over hundreds of iterations. At that budget, you can get fireflies, so these isolated noise spikes that the metric can misread as glare sources. So here in this mask, you can see that there's peppered spots in the raw mask that the metric can misread as being a glare source. So our fix is physically motivated. We convolve the luminance with a point spread function of the human eye, the intraocular scattering that makes bright lights bloom in any scene. Concretely, we use it as passes of a small 3x3 Gaussian. So this is after one pass, most, or if not all of those false positives are removed, and ends up acting as a low pass filter, which the noise dissolves from one pass to another, and the glare mask becomes coherent. It's not necessarily just an ad hoc denoiser, but we utilize the eye-zone optics to stabilize gradients. The second ingredient handles the discontinuities itself. So we replace the hard greater than 5 background luminance test with a logistical sigmoid, so a soft mask that assigns each pixel a glare weight between 0 and 1 based on how far its luminance sits above or below a specific threshold. The parameter k here controls the steepness of that sigmoid, so it's the gain inside the exponential is the coefficient of the contrast term. It sets how sharply the mask transitions from a high threshold to no glare, basically. So here you can see going from k equals infinity, which is just the hard step function, to a softer evaluation of the sigmoid, which shows more regions as being a glare hotspot that the optimizer and the differential renderer can use in their gradients. So together with the point spread function, it gives us a smooth loss landscape where the point spread function fixes the noisy input and the sigmoid fixes the discontinuous threshold. So in our experiments, we optimize in 3 different radiometric domains. The first one is on source side, so specifically targeting the emitter radiance, which we use as a texture on the emitter. We're trying to emulate a gobo mask, so people putting individual slots like blockers in front of an emitter. And the second one is on the boundary side, trying to imitate an anti-reflective coating. So we're optimizing the index of refraction and a spatial blend mask as well. And then lastly, on the surface side, we're imitating anti-glare coating, so roughening the microfacet alpha to diffuse the highlights in the texture, in the scene. And we show that it works across all 3 domains. So here on the left is the before, and on the right is the after. The renders are a little hard to see what's going on, but in the luminance maps, we're trying to specifically reduce the highlight of the glare threshold, which is that bright spot in the middle of the sphere. And it's stable across all those parameters as the optimizer is fed the gradients and it descends to a specific target UGR. And it scales, because we're using differential rendering, it ends up scaling far past derivative-free baselines, such as CMA, ES, or PAL, which quickly fall over as the parameter count increases. So one part that surprised us in our experimentation was that if you take surface roughening, so here we're trying to roughen the surface of the floor of the scene. Rougher means more diffuse, which potentially should mean less glare. At first, that's true. Here we plot what happens to UGR and background luminance as the floor becomes rougher. The UGR, the blue curve, initially goes down, but then it bottoms out at around about 0.2, 0.19 alpha, and then it starts to climb back up. So here the over-roughening is actually starving the room of ambient light, and which is the red dash curve of the background luminance, which is causing it to fall. And because UGR is governed by 1 over the background luminance, the denominator from earlier, the darkening the room makes the score actually paradoxically spike. So here you can see it specifically in the glare masks, where as the floor is becoming rougher, the room is getting dimmer, but the glare masks are starting to re-trigger on surfaces that were previously comfortable. So whether you fall into this trap really depends entirely on one implementation choice. Do you let the gradients flow through the background radiance, or do you detach it? If you detach, the loss basically just goes back to becoming a standard luminance optimization on the hotspots, and the optimizer happily overfrosts into a dark room, so the red curve here. And if you keep the background radiance attached, the loss becomes contrast aware, and the optimizer is penalized for killing the ambient light, so it finds a comfortable equilibrium. The self-regularization here is essentially what makes it work, and it has no analog in the luminance-only optimization. So this all isn't just perfect, of course. There's more to be done. There's some limitations. So the attached versus detached choice is currently just a manual one. We detach for localized textures and attach for global surfaces. The reason why we detach for localized surfaces is because the optimizer can cheat and de-overfrost parts of the texture in order to increase ambient background luminance. But automating it via some sort of localized estimator is one potential future work, and the user also still just picks which parameters to expose. So a layman like myself, I don't know which parameters or materials I would want to use to reduce glare, but maybe a lighting engineer would. But potentially an automated sensitivity analysis would help someone with not as much understanding pick which materials to use. This is also just an inverse design tool, not necessarily a manufacturing tool. So integrating with real materials would be an interesting application in the future. And currently we just optimize for one single viewpoint, and extending this to multi-viewpoints or view-independent glare is another potential future work. So to wrap up, we make UGR, Unified Glare Rating, differentiable with two ingredients, so the eye's point spread function and a soft sigmoid, turning a perceptual rating into something that actually drives inverse design, and we show it's stable across source, boundary, and surface domains. The code is available. Thank you for listening. Happy to take any questions.
Thank you for the presentation. Are there any questions in the audience? Otherwise, I can start. So, yeah, this is very interesting work, right? And it shows kind of a new domain in which we can apply differentiable rendering, kind of architecture and interior design. Do you see other problems in that space that could benefit from differentiable or inverse rendering? Like other visual aspects that could be optimized or other metrics that could be interesting?
So yeah, here we just picked UGR, but you can extend this to any other perceptual or psychovisual metric, and UGR is just one of the things that's defined in CIE, but there's many different ones. And then I think another interesting application would be taking this sort of metric and then applying some sort of larger constraints on that metric. So perhaps the cost of using these materials, or the cost to human eyes of using these materials. Some other constraints would be also interesting. And then perhaps taking that a little bit outside of architecture, but making particular scenes look good to humans, and not just glare, but also color and any others as well.
Great. Great talk. I was wondering, in your literature research or from your background knowledge, have you seen people considering stereo for glare in a certain way? Because I personally would be of the opinion, if you have just a bright spot on a diffuse surface, say like just some light shining at the surface like that, compared to specular highlights, which do look different to your eyes, that leads to different levels of discomfort and different glare. So it's not so much about your optimizer, it's really just, I wonder if the literature has identified that, because we as graphics people, we know this very well. Have you seen that?
Not really. It's fairly extensive, and there's lots of these papers, and I'm sure one of them probably goes into it. Likelihood, yes, but I haven't seen it myself.
Yeah, so maybe graphics people then can feed back also to like device new metrics. Or,
yeah.
Okay, thank you.
Any other questions? We have time for one more. Otherwise, let's thank the speaker again and go to the last talk.